Good afternoon, everyone. Thank you very much for joining us for our third webinar of the i4Driving project. I noticed that we do have some of the participants from the other webinars, so thank you for joining us in our series. Next slide, Vincenzo. So just a few notes, as usual, about the i4Driving project. This is a research project that we started in 2022. We are about to finish next month the project. And you can see on the right the different partners that we had in our consortia, from Tier 1, from OEMs, research institutes, academia. And next slide. We had the vision to lay the foundation for the new industry standard methodology to establish a credible and realistic human road safety baseline for the virtual assessment of the CCAM systems. And our objective is to develop this library of credible models that can be used and reflect the heterogeneity of the human driver behavior. This is how we have the project organized, the workflow. So the central piece is these models that we have been developing. And we started by gathering evidence from human factors from data. And then we had, for validation and calibration, driving simulation and experiments as well. And all of that is being validated, calibrating in our models and tested in some applications. And this is the third webinar, but again, I would like to invite you, if you haven't registered for the upcoming webinars, please, you can scan the QR code. And there's still a set of webinars every Friday, lunchtime until the end of March. So today I'm going to immediately I will introduce our speakers. So we have our scientific coordinator of the project, Vincenzo Punzo, from the University of Naples, and he will tell us about the methodology that was developed to assess and compare the longitudinal driver models. So Vincenzo, up to you. And in the end, we will have the usual space for question and answers. So please feel free to write questions in the chat, and then we will invite Vincenzo to provide the best answer. Vincenzo, please.
Thank you very much, Maria, for the introduction. I hope that the connection is good because I couldn't hear you for some seconds. So please interrupt me if you see any problem. So, okay, so today we will see how we progress and we develop the methodology to assess and compare longitudinal driver models. So where we start? So first of all, as Maria was saying, the main objective of this project was to set a credible human road safety baseline. So some models which could be used as a benchmark in the assessment of automated driving function. And so in order to do this, we thought to make the most of existing models, of course, and we started from physics-based law-driven models, which unfortunately are collision-free and basically do not capture causal mechanisms which lead to accidents. So because we are concerned, of course, with road safety, and we had to enhance these models, to augment with these models with the main factors which affect road safety, which are perceptive and cognitive processes. But of course, we have plenty of competing theories in the field literature. And so the main problem here is how to choose these theories, how to compare models and their performances. And so the two basic questions that we try to answer with this study along the whole project duration is how to assess model credibility. And of course, the corollary is that does increasing model complexity imply more credible models? But of course, we know that this is a rhetorical question, and because we know that when the complexity of model increases, also the uncertainty due to the complexity of the model themselves itself and to the parameters increase. And so what we observe is that the model inadequacy error generally decrease with increase of model complexity, but the uncertainty propagation error increases, and it increases, let's say, sometimes in very huge manner, in so-called cascade effect. And so the craft of modeling is to find the compromise, the best compromise, so the sweet spot between the model inadequacy and the uncertainty. And so this was the objective of these methodologies and of this work. So what are the challenges to do this? So first of all, the empirical evidence that we have contains very low level information compared to the complexity of the process involved. Think about, I mean, we basically, in the most of cases, we have trajectories of vehicles, so kinematics, but the process involves complex perceptive and cognitive mechanisms. On the other hand, we have a very low number of veracity tests available to compare models. What does it mean? That we have a lot of, let's say, tests that can be used for understanding whether the model is able to perform some basic, let's say, behaviors. And so we have, for instance, for longitudinal driving model, car following models, we have the rational driving constraints. We know, for example, that the steady state relationship between speed and spacing has to be an increasing function. So we know a lot of requirements, but whatever model that satisfies this requirement is not necessarily a good model. And so we lack really risky tests to refute our theories and to compare the models. And one more thing is that the methodology to compare models, which is usually applied in field literature, is based on absolute error quantiles or distribution. And we show here that this is fundamentally flawed. And here you see, you have a glance about this. So you see three diagrams. In every one of these diagrams refers to a different trajectory data set. And you see high D and Zen from three different continents. And on the y-axis, you see the goodness of fit measures, so basically the performance, the calibration errors, and the five models are on the x-axis. So basically, you see that all the models behave very similarly, and all the differences that you can appreciate is across different data sets, but within each data set, basically the model seems to be the same. But this is an artifact of the way in which we are investigating and representing the data, because when we compare distribution of absolute errors, the problem is that every single model behaves differently. So every single model, let's say, is able to reproduce better some trajectories than others. But the trajectories which are best represented by a model are not necessarily the same which are best represented by other models. So when we calibrate a model across different trajectories and different data sets, what happens basically is these errors compensate for each other. And so you see very similar distribution, but this is an artifact because we will see that actually the models are very different and they are very different performances. So before going to the core of our methodology to assess model, I would like to give you a very quick wrap up about the calibration methodology, because calibration methodology and calibration is and the impact of calibration in the results of model assessment and comparison is the impact of, let's say, of technicalities of calibration is really underestimated in the field literature. And so many settings and many wrong settings are applied, and this really is a problem for the progress of the of science in this field. And so Calibration problem is clearly an optimization problem in which we want to minimize the discrepancy between observations and simulations, subject to some constraints. And we have 4 dimensions to investigate, basically. So the trajectory data, the optimization algorithm, the measure performance, and the goodness of fit function. We start with trajectory data, and these are to establish references in the field in which we investigated the accuracy of data. And these are some consideration useful. I will not lean on this, but just let me stress that they seems and they are actually trivial, but they are very important for results. For instance, if you look at the last point, if you do not have the same numerical integration and differentiation scheme in measurements and controlling simulation, you are basically introducing a bias into your calibration. And when we move to optimization algorithm, we need, of course, to validate our algorithm, and this can be done by laboratory experiments, which is also the way in which we progress in this work. In this case, you can use synthetic data which are generated by the model itself, and then you can see whether your algorithm is able to rediscover the original parameters which generated the data. And in particular, we use these to look for the best setting of genetic algorithm in this investigation. And then we need to make other 2 very important choices that are the ones of the measure of performance and goodness of fit function. And they are entangled with each other. So these are 2 references. In the first one, we investigate the first problem about the MOP, and in the second one, instead, we combine the 2 problems in one. So the starting point is that, of course, our models are always imperfect, and so we can never reach optimality at the same time on spacing, speed, and acceleration, our primary, of course, measure of performance. And this basically means that we are in presence of contrasting objectives, and so this is the Pareto optimization problem. And we need to decide either we can apply let's say, a Pareto optimization framework, or if we need to decide which of these measure of performance is the best one. So I will not go into the details, but just intuitively, these diagrams show the reason why speed is not the appropriate measure. And so you see here in black an observation, so the speed profile observed, and 3 other speed profiles, flat 1 and other 2s. And we could agree that maybe the best one, which is closer to the simulated to we observed one, is this one, which has a speed drop, and is the closest in time, which has the speed drop. And we could consider worst the flat one, which is not able to reproduce this speed drop at all. Well, if we apply whatever statistic, whatever metrics to calculate the distance between observation and simulation, where the speed does not allow to have a consistent ranking of this speed profile, simulated speed profile. And the thing is immediately solved if we instead use the spacing, because in this case, the spacing is the integral of the speed, and so we have somewhat a memory of the errors in time. And so we have demonstrated that basically if we calibrate on speed, we obtain, of course, an optimal results for speed, but indeterminate for spacing. So we can have a very good speed profile, but with a spacing which is very far from the observed one. While when we calibrate on spacing, basically we are calibrating on not only the speed errors, but also their time convolution. And so we are also, let's say, looking for the best allocation of time in time of the speed errors. And so in this case, we would have, by calibrating on spacing, of course, an optimal results in terms of spacing, but also a suboptimal results for speed. And we validated this with experimental data. Well, so in conclusion, we can say that the spacing is the Pareto efficient measure to be used in calibration of these models, and the other two are dominated by this one, definitely. So then we still need to identify the best GOF, so the goodness of fit function or discrepancy, let's say function or whatever you want to call it. And in the second study, we performed a very extensive study comparing several of these measurements in a Pareto optimization framework. And we were able to identify basically the settings which are not good. And so that have not to be used at all. And we found also, let's say, the most efficient Pareto objective function, which are basically the normalized root means per error and the U of tails. And so this is the setting that we use in all what we see later. So now we are at the core of our presentation. So we start with the framework. And so in this flowchart, you see the three main blocks of our, let's say, methodology for assessment and comparison of models. So in the first block, we have what we call the incremental complexity model design, which means that we want to, say, evaluate the impact of every single human factor add-on to our models. And to do this, we basically perform a full factorial design, which lead us to evaluate and compare a huge number of different models. This comparison was made by, in the central block, which include calibration, uncertainty, and sensitivity analysis. So basically everything is run in a Monte Carlo framework in which we sample trajectory and parameters for every single model. And then we have two different flow and two different, let's say, experiments. One is for evaluating non-safety critical, so nominal driving condition, and the other one is to evaluate safety critical driving conditions. And then by using the, let's say, the synthetic measurements that we have devised, so the so-called model verisimilitude, total sensitivity indices, and collision rates, we basically arrive to a selection of the candidate models, because of course we are not looking for the best model a priori, but we think that it's reasonable to look for, let's say, a selection of a sample of models which behave at best. And so let's start with the left flow, which is about non-safety critical driving conditions. So again, here we look for the sweet spot, which is the compromise between model inadequacy and uncertainty propagation errors. And we will do this applying two different approaches. One is, let's say, driven by this new measure that we proposed, which is the model verisimilitude, and the other one is done by global sensitivity analysis, and so global sensitivity indices. So let's start with the first, let's say, so with the model verisimilitude and the, let's say, the performance, the assessment of model performances. Well, what we did is to, we were basically inspired by the work of the philosopher Popper, which is very well known and fantastic contribution about the epistemology, provided, let's say, a criterion for potential satisfactoriness of a theory. And basically, we could summarize this by saying that it characterizes preferable the theory which tells us more, which means a number of things. So the theory which contains the greater amount of information or content, the theory which is logically stronger or which has a greater explanatory and predictive power. which can therefore more severely tested by comparing predicted facts with observation in one, and overall, in one word, one which has a higher degree of empirical content as Popper defined it. And so you see below some experiments of what does it mean. But I would like to stress here that these considerations and the following one are not really ornamental. So this is what actually inspired our technical contributions to arrive to new and let's say to new measures to assess and compare models. And so what Popper does is to combine the idea of an unachievable truth with that of an empirical content. And so let's say the good quality, I would say, of a model. And he combined these two concepts in one, which is the concept of model verisimilitude or theory verisimilitude, which is the idea of the degree of vector correspondence to truth or of greater likeness or similarity to truth. Well, how did we operationalize this concept and this idea of verisimilitude? These are the key ideas behind our proposed measure. So, first of all, let's say fundamental to epistemology of Popper is the testing of models. So, testing means testing a model of theory against a very risky test. A test is risky when once it is not satisfied, means that the theory can be refuted. And so we thought that a meaningful test for our models, of course, is a calibration against unobserved trajectories. And of course, the higher the number, the higher the heterogeneity and the completeness of our trajectories, and the higher the riskiness of our test. Third point, and this is, I mean, already talk about this, we start from the consideration that distribution of absolute calibration error is unsuitable to compare and assess models. And so we move to a so-called pairwise comparison in which we compare each model with all the other. And we do this by using error differences. So not just the absolute errors, but the error difference to the minimum. So to, let's say, to the lowest error made by any other model for the same trajectories. And in order to be able to compare results from different data sets, we adopted another, let's say, version of this error, which is a normalized error difference. And the main concept here is that basically we consider the lowest error in a test, so in trajectories, corresponding to the highest empirical contents. This is to reconnect with the Popper framework. And so we introduce now the verisimilitude starting from the basic statement, which is really trivial. Our, let's say, basic logical statement is that the model I is better than model J if this error that we will define later for model I is lower than that for model J. And of course, also the contrary is true. But our truth statement is that the model has to be the best. And so we want that the model in each pairwise comparison against the other model is solved with the best, because basically we want that the model outperforms all the other models in the field literature. And so we can straightforwardly define the truth content of model I as the number of times in which it is the best model, and the falsity content, the one in which the number of times in which it is the worst. And this leads to the very basic first definition of model verisimilitude, which is the difference between the truth content and falsity content of the models as soon as desired. But now you may say that this is a very basic approach which does not allow to understand quantitatively how much a model is better than another. And so we introduce a second verisimilitude measure, which, starting from the same premise that we want to see how much a model improves upon the state of the art or degrades relative to the state of the art models, where we calculated these two quantities that are the cumulative errors, or better, let's say, cumulative error differences between pairwise difference between each model. So from a model when it is the best compared to the other models and when it is the worst compared to the other models. And so we can again define this second verisimilitude measure as the difference between these two cumulative errors. And now let's see how we apply these to our models. We start first with the base model. So this is a first, let's say, demonstration of the methodology. And then we will see how we augmented these models with human factor layers and we applied to, let's say, the full experimental design, this approach. So these are the normalized error metric that I wanted to show you. So we started from the consideration that it should not be an absolute error value for the already mentioned motivation. It should not be the percentage error variation relative to the minimum. Otherwise, we would overweigh trajectories which have a very low error. And also we need to normalize over an interval in order to be robust to outliers and to be able to compare across different data sets. So this is the resulting error that we used in our verisimilitude framework. And these are the starting, let's say, the base models that we applied. So they are all models very well known from the family of the very well known and renewed IDM model from Treiber. So they are the IDM, of course, the IIDM, so a variant proposed by the same Treiber and Kesting, and the IDM plus, the IIDM plus, and another version which is new, we introduced in this work and we call modified IDM, which is basically a variant of the IIDM plus. And these are the trajectory data. This is important to stress that it was very hard to select appropriate trajectory data because we needed, let's say, complete trajectory data. So the trajectory data which contain full acceleration and deceleration maneuvers, and also where, let's say, did contain so did not contain lane changing and it did not contain, let's say, other vehicles others than cars and other requirements that basically restricted a lot the trajectories available for the study when we looked in public available datasets. And so you see a sample of the trajectory that you use from the NGC datasets, another sample from the ID datasets, and the third sample from same data, the Japanese datasets, public datasets. Well, now these are the results, and you already have seen this diagram before, but it referred to absolute errors. And you would remember this was, let's say, the comparison with the absolute error values. And you see here, you cannot basically distinguish within each data set the results for the 5 different models. But this is not the case with our error differences. And you see here that basically the MIDM model is by far the most, let's say, the best performing model. It outperforms the other models consistently in all 3 data sets. You see especially in this box plot, that the median is practically zero. And because we are computing differences of, let's say, of the goodness of its function of that model with respect to, let's say, the best goodness of its function, the lowest goodness of its function for all the other models, this basically means that having a median which is zero, it means that at least in the 50% of trajectories, this model performs better than the other. So you see how this approach has allowed us to reveal, to unveil the differences between the model, which actually are quite significant. And this is instead, let's say, the normalized calibration errors. I'm showing you the three different datasets, but actually I could have shown just one. Because the idea was just to have this measurement in order to have to be able to compare errors from the different datasets. And these are the results in terms of verisimilitude scores, which is a very synthetic measure then to compare models and to, let's say, to rank model performances. And so you see that the two verisimilitude measure, this table refers to the ngSim data. They are consistent, and so they both point at the best, the same best and the same worst model. But of course, they could also give different indication. For instance, in this case, for the ID dataset, you see that concerning the, let's say, the second verisimilitude, the IDM plus and the MIDM have quite similar results, despite, let's say, the IDM plus has a very low number of trajectory in which is the best. And so as a poor performance according to the first measure of verisimilitude. This means that this model, in the few cases in which perform better than the others, is performing much better than the other. And you see this by the cumulative positive error difference. And so, I mean, we could, of course, stay a lot of this data, but I just want to stress that when we put all the data sets together, what we observe that the two measures do not give the same result. So they are consistent concerning the best model, but they are no more consistent when we look for the worst model. And so we see that even for the first measure of verisimilitude, the IDM and the IIDM are very similar. When we look at the quantitative performances, the IDM is by far the worst performing model. Well, so far we take a look at model performances, but of course this is just half of the story, because we want models that are not only, let's say, good, let's say, performing, and so have very high accuracy in calibration tests. Because of course, and we would see this when we will increase parameters, this could also be due to overfitting. And so what we want to see is also the robustness of these models. And to this end, we applied global sensitivity analysis. So global sensitivity analysis is very well known as a way of understanding, let's say, having an understanding of how the different uncertainty in our modeling process, could they be, let's say, the model resolution levels, the parameters, the model structure itself. So whatever factor that enters in the modeling process. So sensitivity analysis is able to understand how these individual factors contributed to the overall uncertainty of the model. So it is basically the feedback process in a Monte Carlo framework simulation. So let's try to understand very quickly how does it work. And so basically you see in this matrix on the columns, the factors. So we have the trajectory and we have the parameters. And then, of course, the number of rows is the number of our experiments. And once we have run our Monte Carlo simulation, we get these n results. And particularly here, we adopted not, let's say, generic key output, but we computed the distance between our output, our measured performance, and one observed. So this is actually an error. Our output is an error. Now, if we plot these errors against each individual factor, we can understand intuitively, so graphically, how that single factor affect the output. And so you would recognize immediately that for this second factor, so when we project the output y against this column here, we get this shape, which of course is telling us that this factor is very influential on the output because it is able to give a shape to the simulation results. So when we move from lower values to higher values, the output completely change. And so this intuitive notion is transferred to sensitivity index in a very simple way. Of course, I just wanted to mention that the points here are the same in the diagrams. They are always this y column here, of course. Then how translating this intuition into numbers? Well, we can divide our, let's say, our simulation results, and so our range in 20 vertical bins of 50 points. In this case, we had 1,000 simulations. And for each one of these bins, we can calculate the average value of our simulation output. And so you see here that we have basically a completely different behavior. But if we if you want to define, let's say mathematically, this every single point, we immediately recognize that it is, let's say, an expectation. Of course, this is the way in which actually we calculated it. So basically is the expected value of the output y conditional on the value, on the specific value of the factor. So when we fix this factor at this value, of course, this is the average here, overall the other parameters. And what we can say is that if we compute the variance of these expected values, then this is a measure of the variation over the slices of the expected value of the output y within each slice. And so if we normalize this over the overall variance of our output, we have the so-called first order sensitivity index. And so you would immediately recognize that the variance of these points is much less, almost zero, and is much less than the variance of these pinpoints. And so this translates our intuition that this factor on the right is more influential than the factor on the left. And so we can further elaborate on these in order to calculate also another index, which is the total sensitivity index, which also accounts for the interaction of, let's say, interaction of one parameter, one factor with the other factors. And so how did we apply? So in our framework, basically we sampled parameters and trajectories, and we calculated after simulation the normalized root mean square error on speed and spacing. And if you want more information about this approach, you have this paper from 2015. And these are basically the results for our 5-base model on the NGC datasets. So what you see here is that we have sampled, so one of our factor is the trajectory, so the input trajectory of the leader, and also of the, let's say, of the ego vehicle in order to calculate the error, and the other parameters of the models. So what is the difference between these factors? Well, we can say that the trajectory factor tells us how much of the error variability depends on the input trajectories, which is something, of course, we cannot control because it is simple. The driving conditions, so the, let's say, surrounding condition that the driver will face when driving. So, and while what we can control is, of course, the model parameters. And so in this case, the let's say the indices of the parameters tells how much the error variability depends on the input parameters, and we want to we would like that let's say the variance explained by the parameter actually was as high as possible, and because we can control this variance, it means that the model can be improved by changing parameter, and that is very sensible to the change of parameters. When instead the factor, the input trajectory factor, is very high, it means that there is an important part of the output variance, in this case of the error variance, which cannot be explained by the parameters of the model itself. It just, as it is due to the trajectories that that feed the models. So the input trajectory that feed the model. And so we basically propose this trajectory index, trajectory factor index, as a way of a proxy for the model predictive error. So the lower this trajectory index, the higher, of course, the parameter indexes, and the higher is the model predictive power. And so what about the results? And if you go back to this, you see that basically the lowest values for this index is given by, let's say, the MIDM model together with the IDM. I see that the time is very, very short. So we skip the results, and this is the final, let's say, combination of our results. In this, you see we have combined the model inadequacy error with the uncertainty propagation error given by the just proposed measure, so the trajectory factor index. And so you see that by quantitatively combining these two, we can obtain, let's say, our best compromise. And so a model which is the best performing, but also which is enough robust. And you see here that the MIDM model seems to be, let's say, the best compromise, the one which achieves the best compromise. But it's I really missed a lot of things to do yet. So let's go very fast. So starting from this model, we augmented our models with human factors. And we did this in incremental augmentation framework because we wanted to, let's say, understand the impact of any of these human factors. And we run let's say, a full factorial design. And this is the whole modeling framework. You see, basically, these are the basic models we have talked about so far. And these models receive as inputs let's say, the perceptions, the perceived inputs as modified by perception and anticipation block, and they provide the acceleration command augmented with the cognition and adaptation block. So the acceleration command, of course, changes state of vehicle kinematics, which in turn provide the inputs for the following instance. And so what we tested is, of course, the 5 base models that I've shown to you and 3 perception delay models. Sorry, a layer of perception delay, and so 3 perception delay models, 2 temporal anticipation models, 4 perception error models, and 2 spatial anticipation models. And finally, 4 adaptive driving models. So we ended up with 800 human driver model variants. And you can see in this raster plot, let's say, the activation mechanisms of all these human factor layers against each one of the models. And you also see the number of parameters plotted here as a reference. So these are some numbers. Of course, we run extensive testing, and so you see here quite high numbers, especially in terms of simulation. We run 30 billions of simulation, but these are, I mean, just to get the final results, but we run much more in order to set the methodology. And these are the results in terms of 85th percentile of calibration performances versus the number of parameters. We cannot really stick on this, but this is the results in terms of the model verisimilitude. And you see here how these synthetic measurements allows us to immediately identify a bunch of models which outperform the other in terms of performances and then accuracy. And in this table, you can see how individual human factor layers contribute to the performances, to, let's say, to the improvement of performances of the base model. And these are just relative to the NIDN. And for instance, we can observe that the best compromise, if you want to add just one single human factor layer, the best compromise is achieved by adding the multi-anticipation layer, because with just 2 parameters, you obtain an increase in model performances by 20%. Then this is, again, a way to weigh both the adequacy or inadequacy error and the propagation error. And so you can look at the green, I say at the green value, and identify the model which are basically the most, let's say, the most, as the best compromise between accuracy and robustness. And then let me just say a few words about the safety critical conditions when, as measure for the safety critical condition, we consider the collision rates. And so we ran extensive Monte Carlo simulation, and what we could observe that, first of all, we identified some models which are collision-free, and we tested this by imposing a very high deceleration to all models and sampling parameters. But in other runs, in other Monte Carlo experiments, in which we sampled trajectories from thousands of thousands of trajectories from several data sets, where we observed very high unreasonable collision rates. And the analysis also allowed us to understand which of the human factor layers most contributed to these unreasonable results. And this is very important because, of course, this is telling us that the way in which we calibrated the model, which is just, of course, just on, let's say, optimizing, minimizing the distance from the observed kinematics and nominal conditions, is not well representing the, let's say, the results in terms of safety critical conditions. And we made a step further because we investigated the distribution of the parameters which are causing the collisions, and we compared into these diagrams, let's say, the importance of the parameters, both for the nominal condition as given by the sensitivity analysis indices, and their importance as to the safety conditions, so their ability to let's say, to influence, to provide collisions. And the important result here is that the parameters which are most, let's say, more important are the same both for nominal condition and safety critical condition. This means that basically we are facing with a Pareto optimization problem, and we cannot increase performances in safety critical condition without decreasing the ones in nominal conditions. And finally, we also validated, let's say, the best model against emergent traffic flow characteristics. These are the, let's say, distributions of wave speed against 3 observed data sets. And these are the distributions, the fundamental diagrams for, let's say, 2 models and with human factors and basic MIDM models. And we basically verified that 2 models, and especially the 1755 model, are sensibly improving the based MIDM model, also in terms of emerging traffic flow characteristics. So I really go very fast over these results, but if you want more details about these results, you just need to wait a bit for these papers to be published. This will be presented at the International Symposium on Transportation and Traffic Theory, and has been accepted for publication in Transportation Research Part B. And that's all.
Thank you very much, Vincenzo. It is always a pleasure to listen to a professor. We already have some questions in the chat, and in the meantime, everyone is welcome to address the questions. You can also raise your hand and I can allow the microphone and you can speak, or you can write them in the chat. So if I go to the first one, Vincenzo, you mentioned that the method of model comparison was inspired by Popper's theory comparison ideas. When I hear theory, I envision a method of description of a phenomenon based on the first principles. In that sense, all the models we saw today seem to come from the same theory, since they are all variations of IDM. Could your method also be used when the models come from different modeling philosophies, say an IDM model versus a ML model or a psychology-inspired model? Would your method tell us which model resembles a human driver better?
Yes. Thank you, Arturo. Thank you, Arturo, for this very nice question. So the short answer is yes, definitely. So we can apply, I mean, if we agree on the, let's say, on the performances, and so if we agree on the, let's say, on the verisimilitude measure to measure accuracy, and to the sensitivity index to measure the robustness of model, for sure, we can apply it to whatever model. So that's true.
Then we have another one. When comparing models, should we prioritize calibration error, or is validation error or on unseen trajectories equally important?
Yes, this is a very good question, because it points to, let's say, the main limitation of, I will not say of the study, but of the, let's say, the field literature here, because when we compare models, we actually should not compare calibration errors. Of course, we should compare validation error. But to do this in our framework, I mean, in this established framework, we should have longer trajectories. So we should be able, of course, to split trajectory in several splits, and to use, of course, one for training or testing and the other one for validation. I mean, there are established methods, especially that comes from, let's say, the training of neural networks to do this. The problem here is that we should have much longer trajectory than we have available here in the public data sets. So we should have followed vehicles for longer time, and so we could, in that case, calculate validation error. What we try to do here to compensate for this lack of data is that we adopted the sensitivity and a global sensitivity analysis framework. So this is a very general framework in which you can sample trajectories and you can also inject synthetic trajectories. And so this is to answer also the other part of your question. So unseen trajectories equally important. Yes, that's true. And so we can compute basically the robustness against several trajectories.
And
then
when you
yes.
evaluated, there was another part on that question still. When you evaluated models, did you consider behavioral soundness in the addition to calibration error and robustness? Not sure if you addressed that point.
Yes, I did not explicitly mention this, but of course, this is preliminary to this analysis. So the behavioral soundness is part of, let's say, a verification process that you make before going so detailed in quantitative assessment of models. But of course, this is also an output of our methodology because, for instance, when we have seen that, just to give you an example, we have seen that models which included the multi-anticipation actually have high number of, let's say, collisions, let's say, which were similar to the other models, while the multi-anticipation should just, help the driver in having less collisions. And so we looked into the formulation and we think to have spotted the reason why this happens. So on the one hand, we have seen that multi-anticipation is the human factor layer, which mostly increase the performances of the model. On the other hand, it does not, let's say, accomplish its main objectives, that is the one of avoiding collision. But we were able to spot the reason why it is not working. So it is a comprehensive framework which needs first, let's say, verification of the behavioral soundness and then a more detailed quantification of the performances.
And then a tricky question. Can you describe some unforeseen circumstances or challenges that you faced during the project? Basically, the main challenges found?
Well, we faced a lot of challenge. The whole project was a challenge. One of the main limitation again was the data, and so this is the reason why we also collected other data on driving simulators. So in that case, we have much longer. But of course, we are gaining something in terms of length of this trajectory data, but we are losing something in, let's say, verisimilitude of this data. So data and treatment of data, as always, I think has been the biggest challenge here.
So what would you argue that are the main limitations or the areas that still require some further investigation beyond i4Driving?
So beyond data, thank you, Thomas, for this question, really. Beyond data, for sure, let's say we have to look to the, let's say, to the very last slide that I shown, so to the objective optimization between safety critical condition and safety critical condition. So we need to reframe the whole calibration problem in order to, to achieve good results, both in terms of nominal condition and safety critical condition. This is really the challenge, and this is known to be the challenge, but we have one important result from this project is that we have demonstrated that for this type of models, basically the same parameters are affecting both, let's say, let's say few parameters are affecting mostly both nominal condition and safety critical conditions. And so we need to rethink our calibration framework in order to account for, let's say, both the situations.
Great. And I see that we are already 2 minutes after time. So I think I will take the moment to thank our speaker. Thank you very much, Vincenzo, for all the detailed explanation about one little piece, because there was much more to tell about all the work done there. And I would like to thank all the participants for joining us on this lunch break, and I hope to count with all of you next week on a different topic. Thank you very much, everyone.
Thank you very much. Bye.